Welcome to our colloquium for this week. Our speaker, I expect everyone knows, is David Olive. He'll talk about asymptotically optimal prediction regions. David, we look forward to hearing.
Right. So, predictions done all the time. The next person who comes through that door will probably fit through that door. Maybe this tall. So, it's done all the time. So, you want your investments to do well, and, for stocks, about 45% of your gains are dividends, maybe 55% if they increase in value. And how large will the national debt be? And I was watching TV one time. They said what the average household is, how many households are, and the net worth, and I multiplied it in my head, and the national debt. And it seemed to me that if everybody sold their house and gave it to the government, then the national debt would disappear. When President Clinton, not Hillary Clinton, when President Clinton left office, he had 2 surpluses in a row, and they predicted that the next 10 years would all have surpluses, and we got record deficits in the next 10 years. I'm talking in Iowa City, Iowa, and they told me that there were 200-year floods, within like 3 years. So a lot of people are diagnosed with cancer, so maybe a little bit more serious. There's like prostate cancer and breast cancer. Maybe 80% of the people die of something else. So there, the treatments are fairly good. But there are other. There are other cancers where maybe you have 16 to 18 months to live, you're told that. So that could be a prediction interval. 6 to 18 months. There your standard treatment's not ineffective, and what you might want to do is try to get into a clinical trial, change your population so your success rate might be better. Well, statistical prediction regions, we try to give a guarantee. Same with confidence intervals. If you had an introductory class, you want 95% confidence interval, you want 90% maybe prediction regions. So maybe there's K variables, say K is 2, so you have corn yield and soybean yield in Illinois, hopefully better than last year. And for a 90% prediction region, gather data independently 100 times. About 90 times it ought to have your predicted value in it. About 10 times it should not have your predicted value in that. So, unfortunately, though, the statistical prediction regions aren't very good. With confidence intervals in testing, you have a normal distribution and a central limit theorem. And often, if the distributions have fourth moments, then the confidence intervals in tests also work well, even if your normal distribution is really wrong. So, right, you need fourth moments roughly, so it could be hugely wrong. But when you do prediction, you're really estimating the tails of your distribution. So if you pick a normal distribution, you're estimating the tails of the normal distribution. It doesn't have much spread. If your distribution isn't normal, then you're underestimating your percentiles, and then your coverage is a lot lower. So they're so bad that a lot of disciplines use 50% nominal regions. So there's something called Windsor's principle. It says data in the middle is normal. And think of a highly skewed data. If you cut off the tails, then you can roughly approximate that by a normal distribution. So again, you're trying to estimate percentiles of your distribution. What I want to do is be able to do it without knowing my distribution at all, and then hopefully it'll work for lots of data sets. So I'm going to have independent and identically distributed. That's going to be IID. And I have additive errors, and when you have additive errors, I've been finding regions that seem to work. So what is a prediction region? Well, it's just a set. And I'm going to use a large sample prediction region because I'm not assuming that I know my distribution. And what I want is the probability that it's in that set to converge to the right thing. So if I have a 90% region, I want the probability that my new observation is in that set goes to 1 minus delta. 90% say it's asymptotically optimal if the volume of the region is converging to the population minimum volume regions. So with parametric models like a normal mu sigma squared, it's known up to 2 parameters, mu and sigma squared. And again, these methods tend not to work. So I'm going to have a running example on muscles. I like to say that. And so there are 5 variables. It helps to make, if you plot 2 variables and they're linear, then that's going to help your predictions. I took logs of some of these. So, what might I want to do? A mussel is a shellfish, a lot like a clam or an oyster. Some of the mussels, they have pretty shells and they make buttons out of them. So you might be interested in just predicting the log of the mussel mass. How much of it is there that you can eat? That's the location model. So you have 1 variable, you want to predict that 1 variable. Might want to predict the log mussel mass given the other 4 predictors. You got a big shell, you got a big mussel, so a lot of mussel mass. Might want to predict all 5 variables, that small variate location and dispersion model. I might want to predict the size of the shell and the muscle mass given the other 3 predictors. And I'm trying to predict 2 things, and that's called a multivariate regression. Multivariate linear regression. So a case or observations, that's what you do your measurements on. So here's some data on my mussels. You arrange it into an array. The columns are variables, and then the rows are measurements. So the top row 318, 4.22, those are the measurements on mussel number 1. I'm going to call that case 1 or observation 1. And then the last row, that's for case 82 or observation 82. Tons and tons of things can go wrong besides doing a parametric distribution. So often what you do is you call the data that you've collected, the end cases, your training data, and what you want to predict your future data. They could have different distributions, possibly due to a change in population. There can be population drift. Banks, for predicting credit, about every 6 months they change their models. So there's a student I had who found something in beef, some chemical in beef that was very healthy, so it helped prevent cancer. I forget what it was called. And she was looking at different papers, and one person figured out how to increase this chemical in the beef. And then, once you have someone who's successful, then everybody else is going to imitate them, and then the population would change. So that's kind of what that is. If you're trying to get a chemical or a yield, and somebody's successful at it, then in the next, the 49 who weren't successful, well, the next 25 will use the successful method. So. A little political maybe there. So Reagan, Bush, and Obama spend money like no tomorrow, and then Clinton froze spending. So get different populations there. You could have outliers, cases that are far from the bulk of the data. It could be that you don't have a random sample from the population. So maybe you have 2 hospitals, and then you pick another 3, not at random, just because they're located near to where you are, for example. And maybe they aren't representatives, so your predictions won't work well. And then other model assumptions could be wrong. I mean, just because you put your data into a multiple linear regression model, maybe it's not a multiple linear regression. So you got to check things. And the sample size in might be too small, and when you get into high dimensions, things are very sparse. So if I have 50 dimensions, then I might need 500 cases before I can start to estimate things. If I have 100 cases, then just by chance I might be able to cover that with a smaller ellipsoid, hyperellipsoid than the population one. And then when I try to predict future cases, and I have those under coverage. So, well, what are my, well, first I'll go with the location models. So that's introductory statistics, 483. You have observations from one population. In this case, maybe I have observations of the muscle mass. So maybe I have 100 of them. I'm going to catch another muscle, and I want to get a region for that. So I'm going to do F for the future one. Why do you do that? Well, I want an asymptotically optimal one, so that means I want my coverage to go to what I'm claiming it to be, 90% safe. And then I want the length that has 90% coverage to be as small as possible. So technically getting a prediction region isn't all that hard. If I have a 90%, I can order my data, lop off the bottom 5% and the top 5%, for example, or lop off the top 10%. But that doesn't necessarily give you the shortest one. If you have symmetric data, lopping off the top 5% and top 50% will give you shortest. And here, this is an exponential distribution. Here, if I want a 90% region, I ought to lop off the top 10%. If you happen to have a PDF, what you can do is move a line up and down until it covers the percentage of data that you want, and then that gives you your optimal region. If I had a normal distribution, then that line is going to intersect the curve in two places. So you have little f of A equal to little f of B in that case. And that's how you could find it mathematically if you had a picture, if you knew what your distribution was. But again, I don't want to know what my distribution is and still get an optimal region. So, if I have a bimodal distribution, so two normals, then it would intersect the curve twice, and then your optimal region is going to be a union of two intervals. So. Anyway, how do you get it from the data? Well, suppose you have your data, you can order it from smallest to largest, and then y parentheses 1, that's going to be your min, y parentheses n, that's going to be your max, and y parentheses I is the ith order statistic. And what you can do is, suppose you want to cover C cases, maybe that's n times 0.9 and round it up to an integer. So I want to cover C cases. What I can do is I can go from the first order statistic to the C, then increase by 1, etc., and then find the smallest ones. So smallest of those intervals. And that's called, the smallest one is called the short. They used to do these for half sets, so the shortest half. And as an example, suppose my data is 111, 89, 778, 78, and 76. Order my data, and I want 3 of them. Well, I go 76 to 89 as length 89 minus 76, and 111 minus 78, and 778 over 89. This is supposed to be rankings. They put an extra 7 on the third place team. So third place team got 778 votes, first team 111. I looked up what the actual ratings were, and I saw it was 78. And when you do that, you get 76 to 78. Again, imagine that you want a 90% interval, take n times 0.9, round it up to an integer, and find the short. And that can be used as your prediction interval. And it covers 90% of your cases. If your future cases are like that, then maybe there's a good chance that it'll be in that interval. What I found over and over again, though, is if you estimate your target region, typically it underestimates by maybe up to 5% if you use lots of different distributions. If I have a 90% region, maybe I get 85% for moderate samples. As sample size increases, the coverage performs correctly. I had a paper that came out actually just this month. So in February, And so I've modified the shorts slightly by making it a little bit longer. And what I did is I took a prediction interval for regression and then tailored it to the location model, where location model is a special case of that. And basically what I did is I inflated the shorts slightly by something that goes to 1. All right, for multiple linear regression, again, what you want to think of is I got that log muscle mass, and then I got other measurements on the shell. I want to predict that. So I have a conditional distribution given x. So my predictors are fixed. Someone who weighs 100 pounds is going to be shorter on average than somebody who weighs 160 pounds. So you got conditional distributions. General regression model has this form. And I figured out how to get the asymptotically optimal prediction region, but it was too asymptotic, so I needed huge sample sizes before it worked, except for multiple linear regression. And then that was a 2007 paper. The 2013 paper fixed that. So there are all sorts of models of this Form 1, and neural networks, vector support machines, creating additive models. A lot of these don't have a lot of theory, but they're still trying to get prediction intervals with them, and they basically assume normality and lop off. Well, they try to estimate normal percentiles, and that doesn't work very well. Residuals are going to be your observation minus your estimated observation. And the way you do this is that conditional on x, the yi given x just follows a location model. So if your errors are normal 0 sigma squared and your y is mx plus ei, then your y's are normal mx sigma squared. So the basic idea is try to get a location model prediction interval for your fixed x. But the problem there is that often when you want to predict, you have no data at all there. So what you can do, though, is make pseudo data. So I can take m hat and I can add it to the residuals for my different residuals, and that'll be estimating my location model at that x. And it turns out that you can show that works. So again, basically you take the short of the residuals, and then you add m hat to it, and that'll work asymptotically. But it turned out that the coverage in a moderate sample, realistic sample, if I had a 90%, then it was maybe 85%. You need large samples to get 90%. But for multiple linear regression, it worked. So this is sort of your population prediction interval. Get your population percentiles, and that'll have coverage that's equal to what you want. And then I'm assuming that my m hat's consistent estimator. That'll make the residuals minus the errors converge in probability to 0. And then the folklore is that makes the residual percentiles estimate the error percentiles. It's not hard to show that. That's true for multiple linear regression. And here, the multiple linear regression model, you have your mx as xi transpose beta. So beta 1x1 plus beta 2x2 plus beta 3xp, a linear combination of your x's. And there's something called a hat matrix, and that tells you how far away your x's are from the bulk of the x's, the diagonal elements. And here's the classical prediction interval for regression. And basically, you're solving for normal quantiles. That 1 plus hf goes to 0. That MSE goes to root sigma. That t goes to the normal 0, 1 quantile. And you take a normal 0. You take a mu plus or minus sigma times the normal 0, 1 quantile. That gives the normal mu sigma quintiles. So you're trying to estimate it like that. It doesn't work unless your errors happen to be normal. So, I can replace a t by a z, and then I got a correction factor like this. You can use Chebyshev's inequality and show that the probability is bounded below by this. And 95% intervals, that's like mu plus or minus 2 sigma. So it could be as 95% pi, could be as low as 1 minus 1 over 4, as low as 75%. So what I did instead was I took the percentiles of the residuals and multiplied them by something a little bigger than 1, and then I added those to y-hats. So that gave me one interval, and then what I did is I took the short of the residuals, I'm doing the short again, and added that to y-hat, and then I inflated them a little bit by something that converges to 1, and that gave me my prediction intervals, and then they worked pretty well for moderate sample sizes. So as an example, let y equal height, and then I want to predict it from head length, nasal height, vaginal breadth, and cephalic index. I kind of like this data set because there are 5 outliers, so 5 people were recorded to be 1 inch tall and with head lengths of about 6 feet tall. So 6 feet long. So each head's no stature. What happened was they put the height into the head length. So that means I can take those 5 observations and check them with my prediction intervals and see whether they're in there. I can boot out the outliers or not and see what happens. So that's one of my favorite data sets. All right, the triangles are the prediction interval for each observation. So were they in there or not? And there are 3 cases that they weren't in there. A very good rule of thumb is that your procedure is going to work better on your training data than on your future data sets. So I have 3 out of 82 that aren't covered. And again, if you have 95% coverage on your training data set, maybe you'll have 90% coverage on your future data set. And to some extent, that seemed to work. So, all right, so I guess it's 79 or 96% of the YI were in their intervals. It was a nominal 95% interval, and 3 of them weren't. Another thing to notice is they're approximately parallel lines, and at the population, what you do is you plot mx versus y. So the y equal mx is y equals 0 plus 1 mx. That's the 45-degree line. So this line here is the identity line, the line with 0 intercept and slope 1. At the population, then you take the population short for that value of x, and then you run it up and down that line, and that gives you 2 parallel lines. But here I was using an HF, and that depends on your data and not quite on the fit. But very close to parallel lines, but not quite. Now in the 2013 paper, what I decided to do was just use parallel lines. And what I did is I inflated it a little bit. So again, what I noticed over and over again is when I'm doing a target region and estimating it, if I have a 90% region and I throw in a Cauchy or a log normal or other distributions, I can get as low as 85%. And I don't want it to be, I want it to be close to 90% or higher. So in statistics, when you make your guarantee, you want close to 90% or higher. It's better to have 97% for a 95% interval than 93%. Again, over and over again, as much as 5%. So what you could do is start out for moderate data. If I want a 90, then start out at 95%, and then you decrease it. But if I have 99%, I can add 5% to it. So but the tails tend to be long, so I did like a 99.5% instead. And kind of the motivation. So what my QN is doing is I'm either adding 5% or instead of doing a 99%, I'm doing a 99.5. And then as it increases, it converges to the nominal coverage. And eventually, I just use the nominal coverage. So I use 1 minus delta. And that way I know how much of my data is going to be covered. So these work really well on your training data because I can control how much I cover. I can cover 95% of the data if I want to. And I made it's basically the same thing as before, but I'm using BNs, and my BNs are converging to 1, but they're a little bit bigger. And then instead of using the Schorth, I'm using a little bit bigger Schorth. I'm using the Schorth of n times Qn. So for small n, that might be 95% coverage instead of 90% coverage. So it makes intervals longer. And again, if I have a nominal 95%, if n is less than 20p, then I start at 97.5. Nominal 50%, I start at 55. And then it quickly converges to the coverage, the nominal coverage. And again, the population region is just 2 parallel lines. And in the prediction region, I just estimate those 2 parallel lines. So there's something called an additive model, and you have the Sj of xj there. So S1 of x1, it's just putting a model for your first variable. Maybe it's x1 squared plus log x. Your S2 of x2, that's some other variable, if I'm simulating. But the program doesn't know what those s's are, except you can tell you that you want it to be linear. So I could take S3 of x3 to be beta 3 x3, and then it knows that it wants to fit a linear model. Now, I really have no idea how it does this stuff. It does something with splines and things like that. Not much theory for whether you got consistent estimators or not. Well, I did my prediction region for the data set. Now my point-wise prediction intervals are just given by the lines. So if I get an x and it's here, then this is the prediction interval for it. And again, it worked very well on that data set, and it worked great in the simulations too. So right now, multivariate location dispersion model. On the muscle, I'm going to grab a muscle, and then I want to predict all 5 variables. And what you have is estimators of mean and dispersion. So in the location model, that's mu and sigma. Once you get multivariate, you have maybe a covariance matrix in a sample mean. And there's a family of elliptically contoured distributions where their asymptotically optimal region is are hyperellipsoids. Multivariate normal is a special case of that. What you do is if TC is your estimate of location and dispersion, then you get a distance. C is a positive definite matrix. If that was the identity matrix, that'd just be the squared Euclidean distance. If that's a covariance matrix, then you get ellipsoids where the axes correspond to the eigenvector, largest. The eigenvectors correspond to the largest eigenvalues, which tend to be the regions with the highest correlations. So these things have a nice distribution. You can figure out what their volume is, and then you can see. The key thing is that if I have a hyperellipsoid, and I'm cutting it at h, so my cutoff is distances less than 10. Well, the volume is going to be proportional to 10 to the p. So as your dimension increases, the undercoverage that the parametric regions has becomes really bad. So, suppose the ratio, my H is supposed to be 5, but it's 4. I got 4/5 to the P. As P increases pretty quickly, the volume goes to 0. When you're proving things, adding and subtracting 0 and multiplying by 1 is common. Here I have a distance, and I want to show that it's estimating something at what rate. So I add and subtract mu, I add and subtract what it's estimating, pick out the x minus mu transpose C inverse x minus mu, that's going to give me this thing. And then the other terms, I'll have something that has maybe a central limit theorem, and then they have a written term. And so I only need to estimate my dispersion up to a constant d, and then the percentiles are estimating d inverse, big D squared. And for a multivariate normal, those things have a chi-squared p distribution. I want my distances less than equal to some cutoff, and the cutoff for the multivariate normal is the root chi-squared p. So that's the nominal, and what I did is I just replaced the chi-squared p by the order statistics. So instead of 95th percentile of the chi-squared p, multiply n by 0.95 and round up. That's your order statistic, and now it suddenly should be a prediction region that works for distributions that have second moments, so the volume might be large. So there are kind of three things I want. I want a prediction region with the correct coverage. That's great if I can get that. It's even better if it has smallest volume. And then I want it to work, for realistic sample sizes. Well, you can plug in different consistent estimators, and I'm going to do the classical estimator and something that's called the RMVN estimator, and that gives good estimators good estimates of mu and sigma when you have multivariate normal mu and sigma data. So that came out just in December. So here's some of the prediction stuff. And again, the classical region, it says take your distance less than root chi-squared p. And what I'm going to do is take that same qn and take the qnth order statistic. Again, if I take the 95th 95th percentile of the order statistics, I might get 90% coverage. So I want to inflate it a little bit and let it decrease. And again, that's letting me, I'm controlling the amount of cases that I cover. So if I have a 90% region, I start out covering 95% of the training data set. And again, we know that the feature is going to be less, it isn't going to work as well as the training data set. It seems to be about 5% over and over again when you try to estimate these optimal regions. So there's something called the DD plot, and what you do is you plot the distances from one estimator versus the distances from the other estimator, and then that's going to let me look at these regions. So, all right here, take the normal distribution. It has it looks like that roughly. Spin it around. It looks like a bell. Cut it with a piece of paper. Go up and down. I'll give you your optimal region. Maybe circles if you did the normal 0, 1. And generally you have some correlations. So I think this is like 10, 30, 50, something, 98, and 98%. So there are 6 or so different population regions. And here it's skinny and positive correlation. Here it's fatter with the correlation's not as strong. Then put 100 data points in that. So those are the population regions. And I don't want to assume multivariate normal distribution. I want my things to work under maybe second moments and be asymptotically optimal under elliptically contoured. So again, I have the Buxton data, and I have 3 prediction regions. So I have the classical estimator that uses the order statistic. I have the robust estimator, RMVN, that uses the order statistic. And then I did roughly the chi-squared p stuff. So here I have those outliers, the people who are an inch tall with 6 feet long heads up there, and then I remove the outliers. The theory says that if you have a monovariate normal distribution, then the plotted points are going to cluster about the identity line. So once I get rid of the outliers, there isn't much evidence that against monovariate normal. And then the three regions are very similar. So that vertical line, cases to the left are in the prediction region. The horizontal lines, cases below them are in the region. So, this is for any P, lets me look at it. The cases that are outside of them, aren't in the prediction region. So it's letting me visualize my regions. And also, when you do robust estimate, when you plot two of them, I can check if they're following some line with some line through the origin. That's implying elliptic contoured. So when I have the elliptic contoured distributions, then I can maybe get asymptotic optimality. So I guess these are the sigmas that did that. And then there's the Buxton data. And all right, here's the muscles data, and I did another one. And now, roughly the plotted points are following a line through the origin and where my two prediction regions intersect, and that's above the identity line. So, I don't have monovariate normal data. But if it was covering the identity line right there, I'd have monovariate normal. Now I have like a 4.4 here, and then I can get the classical region going there. So maybe 3.3 over 4.4. Raise that to the 5. The classical region volume's going to be a lot smaller than it should be. So you assume monovariate normality without checking monovariate normality, you're going to have gross undercoverage. So the parametric regions tend to have very strong undercoverage. Right, now, a monolinear regression, now I have my two variables. So I have, I want to get the muscle, and I want to get the shell because I'm going to make buttons out of it. So I have two variables that I'm trying to predict. And what you do is you use the same x's, and then you do a monolinear regression for each variable. So you can write a loop, do a monolinear regression on x and y1 variable, do a monolinear regression on your y2 variables, say x and your predictors. So, matrix form of the models, how do you get residuals from the models? So, how do you estimate the covariance matrix of it? So again, conditional on x. What happens is I've gotten back to the location, to the monovariate location and dispersion model that I just did. So once my x's are fixed, maybe my model follows a monovariate normal distribution. So again, if I had lots of cases at that x, then I could just take those z's. If I had 100 of them, and then I could do the ellipsoid for the monovariate data. Again, typically you have 0 cases, so what you do is do pseudo data, and then my pseudo data, what you do is you take the residual vectors and then you add them to your point estimators. So another way to think of that is take your residuals and make a prediction interval region for it in your hyperellipsoid, and then find my y hat, my point estimator, maybe it's 3 and 4 for my muscles data, and shift that so instead of being centered at 0, it's centered at 3 and 4. And that turns out to give you your prediction region. And those pseudo data are very close to the data that I would like to have. They only differ by a factor of radians. So. Again, if my errors were in M0 sigma, so I have M variables, and the classical region would be the chi-squared region. And basically, it turned out that I was able to use the monovariate location dispersion regions on this data, and that means I could use the software and the graphing stuff that I already had. All right, what's the geometry? Again, get the region for your residuals. So that's a hyperellipsoid. Get your point estimator, your single best value, the estimator of the mean of your of your variables, and then shift that region so it's centered at the mean instead of 0. And again, it's going to turn out, here's my Mahalavs distances, but y minus y hat is equal to epsilon hat, which is equal to epsilon hat minus 0. So it turns out that this is just shifting the prediction region for the residuals to have center of y hat, and then that gives me my prediction region for the y's. And again, if I have a 90% region, then I end up covering 95% of the data points. So you ought to check your models. So I have log of the shell mass, and it's nice and linear there. And then I have the muscle mass, it's fairly linear there. And then now I've made the DD plot with the prediction regions. Before, when I was doing all 5 variables, it was tilted quite a bit above the identity line. Now the tilt's not so bad, but it's suggesting elliptic contour, but not monovariate normal, because it's not varying the identity line. Means that the monovariate normal prediction region, right here, it's cutoff is too small. You raise it, you square that, and it's smaller yet. So residuals are equal to residual minus the error plus the error. The residual minus the error tends to follow a normal distribution. So if you try to check normality using residuals, well, you got a normal component plus the error component. For small samples, the normal component might dominate. All right, let's do a little theory. The short wasn't due to me, so someone showed that the short is converging at a running rate for the length, but its location's not as good. And that kind of helps explain why you have undercoverage. You're getting the length about right, but it's wobbling around, and that's going to be giving you undercoverage because of that. You could actually apply it to discrete data, so maybe I have data at 0, 1, and 7, but there it's going to wobble around some, so you can't really, you can get your coverage correct or higher, but you can't get, it's not going to converge to anything, because sometimes it'll be 0, 1, sometimes 1, 7, sometimes 0, 7. For monocolinear regression, you can show that your residuals minus your error, the maximum is going in probability to 0. Then that's going to make the sample percentiles perform well. And then for general regression models, I just said this, assume that sample percentiles perform well. Does the short perform well? And the basic idea is, if the sample percentiles perform well, then the short eventually, the residuals are practically errors. So it's covering, asymptotically, the short is covering, say, 90% of the errors. And the best region is covering 90% of the errors. So that means that the sample short is going to be longer than the population short, which is the shortest region. Or if I have the shortest region covering 90%, I have another region that's always covering 90%, then that region is going to be longer than it. And then I showed that the short. So I have the probability that the length of the short is less than L is going to 0, but I can show that the probability that the length of the short that's less than equal to L is going to 1. That means that the length is going to the correct thing, and I assume that it's unique, so that means that the interval's converging to the population short. For monovariate location and dispersion, I guess I did some stuff on my RMVN distribution. It's really hard to prove stuff for robust estimators, but there's a theorem that if your TC is a consistent affine equivariant estimator of mu s, and then you apply your classical estimator to the cases that are to half of the cases, then you get a Röding consistent estimator again. So I can do that iteratively, and then that lets me show that my RMVN estimator is consistent. Well, I didn't have to do some of this stuff. So in the monovariate linear regression model, a paper came out just last fall showing that there's a central limit theorem for the estimators under fourth moments, roughly. So my things are going to work under fourth moments. For distances, I just need consistency of my distances. And add and subtract 0, and you can show that stuff. Here's a more general model. So I have my monovariate model. I have my yi is equal to EYI plus epsilon I, and then my my monovariate linear regression model is a special case of that. And then I show that the sample percentiles converge, and I show that it covers Qn% of the cases and things like that. And I did simulations, and I have a 95% region. I want my values between 0.94 and 0.96, etc. So things work. Here the volumes, when you use a parametric, go to 0 pretty quick. What are some things other people are doing? Well, you can estimate the PDF of a distribution, and then you can move up and down. So, I could have data that has a really weird shape, and then estimate that PDF, move up and down, and then get a pretty good region. So that's what some people are doing. Instead of predicting one variable at a time, I could try predicting. I could try to predict k variables. So I want 5 future observations to be predicted correctly with 90% probability. So lots of stuff to be done in univariate and multivariate time series. All right, I'm done.
You're done.
Other questions?
So you did not use a density estimate for it?
No. So the Schorth is very much like getting the highest posterior density region in Bayesian statistics. Right? So it's estimating my highest density region, provided that I have an interval highest density region.
So what happens if the data is like multivariate data? How do you order and stuff?
Yeah. So when I have multivariate data, when I have elliptically contour distributions and I have hyperellipsoids, and then my regions are hyperellipsoids, and I can show that they're converging to the correct things. So there I have asymptotic optimality. But in general, they are large sample regions under maybe fourth or second moments. So I'll have 95% coverage, but their volume could be huge if you don't have the elliptically contoured stuff. So again, you do want to check assumptions. Look at the DD plot. Are they highly correlated about some line through the origin? That's suggesting elliptically contoured. If you don't have that, then you might have a lot higher volumes. So here's log normal, and that's not elliptically contoured. Now I have correct coverage, but I don't have correct volume, and my volume ratios aren't going to 1. If I had elliptically contoured data, then my 2 prediction regions would be estimating the same thing, and the volume ratios would be going to 1. Yeah.
David, much of the language and technique seems similar to pattern classification, and so it's just like a slightly different take on it.
Right.
But could these techniques be used in sort of non-parametric pattern classification problems?
I said that you can estimate the PDF, and then you can cut it, and you can do something very similar to that with pattern classification. So in pattern classification, maybe you have two groups. So you get the density for one group, you get the density for the other group. Then you have your new observation that you want to classify, and what you do is see, which PDF is it higher on. So they are very similar.
Yeah, because the use of Mahalanobis distance
Yeah.
and those techniques is very similar.
Yeah, and I did a robust pattern classification using Mahalanobis distances. It made great sense in theory, and then it works so bad it's not publishable. So
Yeah. But it's the same kind of problems where you're not.
Very similar.
Yeah,
So
you don't know the underlying
yeah.
parameters. I mean,
In
it's,
classification, you have K groups, and then you have a new observation, and you want to allocate it to your group correctly. Here, I sort of have two groups. In or out of my region, I want to get it in the region. If I can.
Right.
Yeah, they're very similar ideas.
When you did this simulation, did you do like mixture, mixture?
Yeah, I did. So an easy way to get elliptic contour distribution is to take a mu sigma and then a mu 100 sigma. As long as they have the same mu, they can have different sigmas, and that gives you an elliptic contour distribution. I did things like that. It looks like what I put here was monovariate. I put in a Cauchy distribution where the moments don't exist, and then the classical estimators have a huge volume compared to the robust estimator. But in the 2013 paper I put in general regression and monovariate location and dispersion. So I did a longer simulation for the regression, and this is actually the simulation that I did for the dispersion. I gave them programs though, so they can simulate them themselves.
Any other questions? All right, well, we hope many of you will join us for refreshments upstairs. Thank you again.